My name is Olivier BODENREIDER. I'm the acting director of the Liste Hill National Center for Biomedical Communications at the National Library of Medicine, and that's part of the National Institutes of Health in Bethesda, Maryland. And I'm delighted to be with you. It's the morning for me here, and thank you for adjusting the time because it would have been a really early start in the morning. So I'm delighted to be here. Thank you for the invitation. And we're going to talk today about, in addition to being to my administrative responsibilities at the Liste Hill Center, I'm also a researcher, a principal investigator in the Intramural research program of the National Library of Medicine, where I do research on biomedical ontologies. And as part of this research, we've been focusing lately on the alignment of biomedical terminologies. And more specifically, we've been looking at this with new eyes, so to speak, using supervised learning to complement or to replace the lexical models that had been used in the past to achieve the same task. So that's what we're going to talk about today. So we're going to go through this is applied to the Unified Medical Language System, the UMLS. So we're going to talk a little bit about the UMLS. So before we go to the outline, a little bit of a disclaimer. That's a mandatory disclaimer. It just says that it's not the US government speaking, it's just me. So we're going to go through a little bit of background about the UMLS Metathesaurus, for those of you who might not know about it. Then we'll see the legacy approach to predicting synonymy through lexical models. And then I will show you the research that we've embarked on that uses supervised machine learning to predict synonymy. So a little bit of introduction. That's a very, very brief introduction to the UMLS Metathesaurus. UMLS means Unified Medical Language System, which suggests that there's such a thing as medical language, that it requires unification, and that's doing so will take a system. If you want to know more, the UMLS is publicly available. There's you need a free license, a no-cost license, but it is publicly available, and you can check it out there. The UMLS started in 1986 at the National Library of Medicine. It was created for two main reasons. The first one, I'm sure you're aware of it, it is that the same medical concept can be expressed in a variety of ways. And unless these ways are, these lexical expressions, if you wish, are grouped together, there's no way a computer can know about what they are. And there's also distribution issues about some of these vocabularies that the UMLS addressed. So at this point, the UMLS contains roughly 157 families of source vocabularies, and I'm not counting the translations here. There are terms in 25 languages, but we'll focus on English terms today. It provides a broad coverage of biomedicine. There's 12.5 million names grouped into 4.4 million concepts and millions of relations among these entities. So if we look at the UMLS through an example, we can take, for example, Addison's disease. So that's an endocrine disorder that affects the adrenal glands. The adrenal glands usually secrete cortisol, but in Addison's disease, the production of cortisol is not sufficient. And for these reasons, Addison's disease is also referred to as chronic adrenal insufficiency or hypocortisolism. And I'm mentioning this because these features show up in the names that have been given to Addison's disease. So these are some of these names: Addison syndrome, Brown's disease, melasma addisoni, asthenia pigmentosa, which refer to some of the symptoms of Addison's disease, the coloration of the skin, the fatigue that goes with the disease, and also other names such as primary adrenal deficiency, primary adrenal insufficiency, primary adrenocortical insufficiency, and chronic adrenocortical insufficiency, which in this case highlight some of the features of the disease in contrast to other forms of adrenal insufficiencies. So the UMLS Metathesaurus takes all these terms, harvests all these terms from biomedical vocabularies, and groups them together when they are synonymous. That's one of the main features of the UMLS Metathesaurus. Technically, it groups all these terms into a concept that gets identified with a concept unique identifier. That's the QUI. And for example, Addison's disease and its synonyms are grouped together under the concept labeled C0001403. To look at this under a microscope, so to speak, we can see that some vocabularies provide exactly the same term, the same string, in which case these strings will still have two distinct atom numbers because they come from different sources, so it's recorded this way. And they are grouped together under the same string number, string identifier, because they are the same string, headache and headache in this case. Other vocabularies will have the plural version of the string, headaches in this case, and they will have, of course, different atom identifiers, and also in this case, different string identifiers, because one is singular, the other one is plural. But since they can be normalized in the same way, we'll see later what normalization means, they get the same lexical unit identifier, which is the Louis, the green part here. They are grouped together in this way. There's another synonym, less common for headache, which is cephalodynia. And in this case, new atom, and since it's a different string, there's a different string identifier. And there's no plural of this, so it's all lexical unit identifier. But all these things are grouped together because, as I mentioned, headache and cephalodynia are synonymous, and therefore they are grouped together in the same concept. So essentially, putting together the UMLS Metathesaurus consists in part of grouping synonymous strings into the same concept. And what we're going to see next is how do we do this and how can we think about this with in new ways. But just to finish up with the UMLS, the main interest in the UMLS, in my opinion, is that it really provides a way of integrating various subdomains of biomedicine through the integration of the terminologies that are used in these subdomains. So, for example, SNOMED CT is used to code information in clinical repositories. MESH, I'm sure you're familiar with it, is used to index the biomedical literature. OMIM, which is online medical inheritance in man, is used to code genetic Mendelian inheritance in man, is used to code genetic knowledge bases. The gene ontology provides annotations for gene products. The foundational model of anatomy is a reference in the domain of anatomy, and you can take, all the subdomains of biomedicine. There's some kind of vocabulary for it, and the UMLS integrates them all. And the alternative to doing it in the way it's done in the UMLS would be that we need to create point-to-point mappings between these sources and more specifically between the concepts in these sources, which would be a daunting task. Instead, the UMLS groups together into the same concept the terms that are synonymous when they are found in the various vocabularies, therefore creating a bridge, if you wish, between SNOMED and MESH, and beyond that, a bridge between clinical repositories and the biomedical literature. So in practice, if you have a medical record coded with Addison's disease using SNOMED, you can, quote unquote, translate it into its MESH equivalent and start a search in PubMed. That's a typical example. Okay, so having briefly presented the UMLS Metathesaurus and the issue at hand, which is how can we create the UMLS Metathesaurus? How can we identify terms that are synonymous so that we can group them into concepts? Let's see how it was done, how it's been done for the past 30 years, which is by creating a lexical model of synonymy. So when we look at these terms, adrenal gland diseases, and the first one and the last one in particular, diseases of the adrenal glands, there are some commonalities, but there's also some differences. For example, adrenal is capitalized in the first term, but not in the last one. So let's say that for the purpose of comparing strengths and comparing terms, capitalization is not really meaningful here. So let's ignore capitalization. We have adrenal gland versus adrenal glands. Well, let's say that singular plural differences are not really meaningful for the most part when we compare terms. Diseases, one is capitalized and the other one is not. We've already talked about this. And then the difference is that in the last one, we have diseases of the adrenal glands. We don't have of the in the first term. But we know that prepositions and articles, determiners, are not really bearers of semantics. They are considered stop words for this reason in information retrieval. So we can ignore them here. When we do this, we have adrenal gland disease if we remove the S, and disease we remove of, we remove the adrenal gland because we remove the S also. So the only difference remains the order in which these normalized words appear. So bear with me here. I'm going to suggest that for the purpose of comparing terms, biomedical terms, it's going to be a good thing to ignore the sort or to ignore the order of words. I wouldn't recommend doing this in text in general because you can destroy the meaning at the same time. But for the purpose of comparing terms in the Metathesaurus, it's been shown to be a good thing. And when you do this, the first term and the last term end up being the same. Once they are normalized, they look exactly the same. And therefore, this is what I've described forms a model for lexical similarity, which it in turn forms the model for synonymy. So we're going to go through this in a little bit more details in the following slides. In order to do this, you need a couple of things. You need a resource that tells you, about the words that exist, and that's what we usually refer to as a lexicon, and the properties of these words. For example, if I take the word headache and I want to have it in the plural, it's going to be headaches. It's a regular English plural. But if I take nucleus and I want it in the plural, it's going to be nuclei because it's a Latin type plural. So this information needs to be codified somewhere, and it's in a lexicon. And there's a lot of other information that gets codified there. So there's the specialist lexicon that was created as part of the UMLS Metathesaurus. It's an English lexicon that's been enriched with words from the biomedical domain. It contains over 500,000 entries at this point. And the properties that we are really interested in for this purpose is morphology and orthography. I'm gonna go through the next slides very, very quickly in the interest of time, and that's mostly for reference purposes. So this tells you that the specialist lexicon encodes information about inflection. That's the singular plural differences dimension when it's for nouns. Derivation, how do you go from a noun to a verb or from a noun to an adjective? It also encodes information about spelling variants, you know, the differences between British English and American English. And all this is useful for normalization purposes because it allows one form to be transformed into the other automatically. This is an example of an entry in the specialist lexicon. The point is that it's, of course, it's machine readable and it's meant to be processed by computers. It's not a dictionary for humans. So the specialist lexicon has supported the development of the lexical tools, which is a set of tools that was developed for to help manage the lexical variation in biomedical terms. And the main tool, so it's useful when you want to create indexes. It's useful when you want to do some of these transformations that I was talking about, but mostly what we use it for is the normalization, which is a set of transformations that are applied to original terms to transform them into a normalized term. And again, the purpose is that when two terms normalize the same, they are candidates for synonymy. So what does normalization look like? Let's look at it for an example. We're picking a new disease, Hodgkin's disease, and the term here is Hodgkin's disease, NOS, which stands for not otherwise specified. And this is a term from the International Classification of Diseases. So we remove the genitive mark, the apostrophe S, because we know it's not meaningful. We remove not otherwise specified because what does it tell you other than you don't know more about the thing? So we consider it a stop word and we would remove the stop words in general. Then we lowercase everything. In this case, the capitalization of Hodgkin was not accidental. It's an eponym, but it gets lowercase nonetheless. We remove the punctuation. We remove the singular plural differences. And we sort the words in alphabetical order, which essentially leads us to the normal form, disease, Hodgkin, all lowercase. And when we do this, not only the term that we started with normalizes this way, but all these terms on the left-hand side normalize exactly the same way. And you can start, so it's a very simple example here, but you can start seeing the power of normalization when it comes to grouping terms together. And of course, in this case, it's not difficult to see that all these terms are synonymous. And I'm not making this up. All these terms you can find in some vocabulary of that you find in the UMLS Metathesaurus. So As I mentioned already, normalization is useful in that it provides a model for lexical resemblance, which can help us find lexical variants for a given term and group these lexical variants together. And that's essentially what helps with the curation of the UMLS when it comes to grouping synonymous terms together and putting them into the same concept. So besides normalization, there's another principle that's used to curate the terms, the biomedical terms, into concepts. So the first principle is what we just discussed. Lexical variants are grouped together when they normalize the same, with one exception. Of course, we don't group together things that we know are different, even when they are lexically similar. For example, if we take nail, the body part, and nail, which is a synonym for a pin that you can put in a bone that's fractured to repair it. We know that these two things are different because maybe they come from different, one comes from an anatomy terminology, the other one comes from a medical device terminology. And in this case, we're not going to force them into the same concept. But it is helpful. This notion of lexical similarity is very helpful. The other principle that the UMS uses for its creation is that some source vocabularies already provide the notion of synonyms among their terms. And this synonymy, when it's asserted in a source, tends to be conserved into the Metathesaurus. But it gets better because you can actually combine these two properties. And so in some cases, you know that, so in this example, the blue groupings represent source synonymy. It's two groups of synonyms that are provided, one by mesh, the other one by SNOMAD. The green groupings represent the groupings that come from lexical similarity and normalization. And as you can see, we can combine information from the blue groupings and the green groupings and derive a broader set of groupings, which is the purple groupings that corresponds to what goes into the concept. So how do we build the UMLS? How is it built in practice? All terms from all the source vocabularies are processed and they are normalized. The terms that normalize the same form sets of candidates for synonymy, and they're going to be reviewed manually. And source synonymy is also taken into account, as I mentioned. All this is going to be reviewed by human editors. And once synonymy is adjudicated, the synonyms are grouped together and assigned the same concept unique identifier. Of course, as you can see, this is, although a lot of it is facilitated by computers, it remains a labor-intensive activity, and of course, it's error-prone because it's easy to miss one term or to group one in error. So, which leads us to: is there another way, and possibly a better way? And this is what we're looking at with when we try to predict synonymy using supervised machine learning. The idea here is that the UMLS provides, it's been built for the past 30 years, and so it provides a large set of positive examples and negative examples that can be used for learning purposes. So positive examples are going to be terms that come from the same concept, because by definition, we know they are synonymous. And negative examples, well, it's all the other terms. If you take two terms from different concepts, you know that they're not going to be synonymous. And of course, if you use deep learning, you can use a variety of features. You can use the words in a term, that is lexical features. You can use the semantics. You can use relations to other terms. In what I'm going to present, which was our first foray into predicting synonymy, we only focused on lexical features, but we've done additional work since, leveraging the semantics and the relations also. So we need essentially to create a synonymy function. And an ideal synonymy function would, so if we look at two concepts here, Addison's disease and Hodgkin's disease, a good synonymy function would take any terms from the first group, and when we compare them pairwise, it would find them synonymous, would label them with a 1. And in contrast to this, if we take any term from the first group and we compare it to any term from the second group, it should find them non-synonymous and label them with a 0. So we created a neural network architecture. We used word embeddings from BioWordVec, which is a pre-trained model. And we used a Siamese short-term memory network. The technical terms are not really important. And we used the Manhattan distance as the similarity function here. So it looks like this, but if you like me, all neural network diagrams look about the same, if you wish. But it shows essentially the series of transformations that you have to do. So you take a pair of terms, you tokenize them, you create BioWordVec embedding for them, and then there's further learning that goes on. And at the end of the day, the last layer of vectors get compared using the Manhattan distance, and you get a similarity between 0 and 1. We take a threshold, and if it's lower than the threshold, we say that it's not synonymous. If it's above the threshold, we say it's synonymous. So that's essentially how it works. But more interestingly, let's see what kind of hypotheses we made when we started working on this. We thought that it was probably going to be more difficult to predict synonymy among terms that are lexically different than terms that are lexically similar. So headache and headaches, that shouldn't be too difficult for any program to see that they are synonymous. Heart attack and myocardial infarction that are lexically different but synonymous, it might be more difficult to find out that they are synonymous. So that was one of our hypotheses. And likewise, it's probably also more difficult to predict non-synonymy among terms that are lexically similar than among terms that are lexically different. And there, that's the kind of things that I was talking about with nail and nail, the words that have different meaning, or cold and the acronym for chronic obstructive lung disease, for example. They are the same string, but they mean completely different things. So we ran experiments and we took into account different degrees of similarity in the learning as well as in the testing. And this just to show you that the numbers of examples that we use for training are high, and which is good because there's a lot of training that can happen, and we have no problem having a large number of examples because, as I explained, we take we can take all possible synonymous pairs by taking terms pairwise within each concept. And the negative pairs, it's even, we can find billions of negative pairs because we just have to pick two terms that belong to different concepts. And so we measure lexical similarity to test the hypothesis that we started with. We measure lexical similarity, and we grouped the terms in high similarity terms, low similarity terms, and terms with no similarity whatsoever to see whether we were able to learn. So when we train and test on the same types of strings, we have good results. Now, what's in real life, we're not going to be able to bin the terms that we compare into these kind of similarity groupings. So what we wanted to see is whether we would be able to train on one type and test on other type, and the learning would transfer across the types of similarity. And it turns out that what we found here is that some models transferred poorly, if you wish. And we actually found that the combination of using terms from high similarity groups, low similarity groups, and no similarity groups actually gave us the best results. And we compared it to a baseline in which we mimicked the role of human curators by applying normalization and source synonymy, as I discussed. And what we can see here is that there's a huge gain in performance from the deep learning model compared to the traditional approach as we could mimic it. So these results were really encouraging. It largely the deep learning approach largely outperforms the traditional approach of normalization combined with source synonymy. We showed that including terms from different lexical similarity groups among the negative examples was key to the performance of this approach. Of course, there's more that we want to do here. For example, we've only used the lexical properties of terms. We haven't used in this deep learning approach. We haven't used the context. We haven't used source synonymy. We haven't used the relation among terms, the sources, and we can do this. Actually, we've done this, and we've showed that it gives a little boost in performance. We want to also use different types of embeddings, and in particular, transformer architectures seem interesting, and we've started also exploring there. And at the end of the day, we need to go beyond an academic exercise because what we would like to do is actually facilitate the work of the curators who put together the UMLS Metathesaurus. And in order to do this, one real-life application would be to use our system for integrating terms that come, the new terms, if you wish, that would need to be integrated as part of a new version of the Metathesaurus. And we started looking into this also. It brings difficulties, but we've made good progress in the recent days, so stay tuned. So in summary, what we've learned is that the UMLS is a very large biomedical terminology integration system, that its legacy, the legacy way of constructing it has relied on lexical features, creating a lexical model for synonymy, and also supplemented by human review. And I hope I convinced you that supervised machine learning approaches have shown promising results when it comes to predicting synonymy and are a candidate for replacing the traditional approaches for constructing the UMLS. So with that, I thank you, and I will be happy to answer questions. If you have questions beyond this talk, or if you want to contact me, there's all my contact information there. And yeah, so let's go to questions.